Hello everyone, welcome to another episode of Math-221. So today we're going to do section 9.5, which is counting subsets of a set, combinations. Okay, so we're going to start off with a motivating example to see what the formula is for combinations and why it works. So first I want you to remember that an R permutation is a particular way of choosing R elements from a larger set and arranging them in a particular order. So for example, if we want to know how many ways there are to assign 3 students from a class of 5 to be on a committee consisting of a president, treasurer, and secretary, then what we could do is we could find all the 3 permutations of the set of 5 students, and then whichever was the first one, we would assign that to be the president, and then the second student, we'd assign them to be the treasurer, and then the third student, we could assign them to be the secretary. And you could change the order of that, but as long as you have some fixed order like that, then that will give you all of the ways of making the committee. Okay, so let's say our students are named A, B, C, D, and E. So here are all of the 3 permutations of the set A, B, C, D, E. So I've just made them all for you in this table, and they're in a very particular order that will be helpful in a minute. But for now, you don't need to know about that. You can just see from the table here that this is 60 different possible committees. So like this committee right here, A would be the president, and then B would be the treasurer, and then C would be the secretary. Or like in this one over here, C would be the president, and then D would be the treasurer, and then B would be the secretary. So the way you get this number 60, if you don't want to make the whole table, is it's P of 5 comma 3. And another way you could do it is you could just say, okay, I have 5 choices for my president, 4 choices then after that for my treasurer, and then 3 choices left for your secretary at that point. So that would be 60. Okay, so a related problem is, what if we want to choose a committee with 3 members, but we don't care if they have any special roles? In other words, they're all just on the committee, they don't have any job titles, they're just committee members. Well, so then what would happen is that these outcomes, which we've considered to be different outcomes before, they suddenly become the same outcome. So in other words, ABC, ACB, BAC, BCA, CAB, and CBA, those would all become one outcome. So it's like this is just one outcome right here. And in fact, I've arranged the table so that each column just becomes one outcome. So this is all one outcome. So previously we were thinking about these people having different roles, but if they all have the same role, then this is just the same committee with A, B, and D on it. And then this is one outcome, and so on and so forth. So each possible committee with no special roles, what I want you to notice is that each of those appears 6 times in the table as it is at present. And that is because there are 3 factorial, which is 3 times 2 times 1, which is 6, ways to arrange any 3 students. So if we take any 3 students, like A, D, and E, there are 6 ways to arrange the letters A, D, and E, which are shown here. But that is what we want to actually just consider one outcome, now that we're not having special roles. Okay, so this is just what was on the last slide again. And then so to find out how many possible committees there are with no special roles, what we can do is take the number of possible committees that there were before when we cared about the order that the students were in or when we were giving them special roles. And then we can divide by 3 factorial, which is the number of ways to arrange 3 students. And what that's going to do is previously we had this table with 60 entries, and then we noticed that each of the outcomes that we wanted was represented in that table 6 times. So what you do is just divide by 6. Okay? So that makes every 6 outcomes just collapse into one outcome. And so you have 10 outcomes in total, and that was the 10 columns in the table. Okay, so there are 10 ways to choose a committee of 3 students from 5 students when we don't care about what order we get the students in. And the fact about the order is corresponding to the special roles. Okay, so if we don't care what order the students come in, we're not going to use that to assign them to any roles. Then there are only 10 ways. Another way to think about this is if you think about the different subsets that you could have from a set of 5 elements. There are 10 different subsets of size 3 that can be chosen from a set of size 5. Okay, so now let's look at the general formula for this situation. Okay, so these are called R combinations. So let n and r be non-negative integers where r is less than or equal to n. An R combination of a set of n elements is a subset of R of the n elements. Okay, and the symbol that we use for that, it had actually appeared previously in section 5.1, but I don't think we went over it at that time. But this is the symbol that you use for that. So this is the number of different subsets of size R that you could choose from a set of size n. Okay, and you read that symbol aloud as n choose R. It's kind of mysterious why it's the symbol looks the way it does. It doesn't really have like a C in it or anything. There is actually another way to write it, which is like this, C of n comma r, where the C stands for combinations or the word choose. And then there's also this way of writing it. You put a little subscript here and then C and then another little subscript there. You might have seen it that way if you took like AP Calculus or something. Okay, and again, that's just the number of subsets of size r that can be chosen from a set of n elements, and then each of those subsets is called an R combination. Okay, and then next we have the theorem that tells us how to actually calculate this number. So it's exactly what I was just going over in that example. The number of subsets of size r, or R combinations, that can be chosen from a set of n elements, which is denoted n choose r, is given by this formula right here. So the first version here, we saw that in the example that I was going over. So basically you calculate how many different ways there would be to do it if you cared about the order that you were getting the elements in, and then you divide by the number of different ways that you could rearrange each set of R elements, and that is to prevent you from the overcounting that you get when you just do the numerator. So if you just do the numerator, then you would be counting each outcome R factorial times. So you got to divide by that R factorial to get the actual number that you want. And then if you plug in the formula for P of n comma r, if you just plug that in, then you get the second formula down here, because the formula for P of n comma r, just put a little note over here. Recall that P of n comma r is n factorial over n minus r factorial. Okay, so if you just plug that in and then you divide by an extra factor of r factorial, then you get that second formula there. Okay, so the formulas, I don't want you to worry about them too much because you can just do it on a calculator or a computer. So over here on the left, there's 3 different ways that you can actually put it into Wolfram Alpha and they'll all work. You can put, for example, 5 choose 3, or you can put C of 5 comma 3, or you can put 5 C3 like that. Either of those ways will work. Those will all give you 10. And then if you have the TI-84, then here are the little instructions there. So this is actually for permutations right here, and then the one for combinations is right underneath it. And then when you put that in, you'll get a little thing that'll come out like a little template like that. And you just have to navigate with your arrow to the right little spaces there, and you put N right there, and then you put R right there. And you can do it on a TI-89 or any other calculator, really. You just have to Google how to do it. Even a lot of scientific calculators actually have this on them. You just have to find the right menu or look up the instructions. Okay. All right, so now what I've got here is this is a summary of all of the different counting techniques that we've learned. We've learned 5 different techniques. And typically people find counting to be pretty challenging because there are so many different techniques and you may have to combine them in a lot of different ways to solve a single problem. Actually, when I was taking discrete math for the first time as an undergraduate, I got super stressed out about all these different rules and I couldn't seem to make them work. I couldn't break down the problems. I was having a lot of other troubles in my life at that time. And I actually had a nervous breakdown shortly after that and had to leave school, which really sucked. But I feel like that was actually one of the things that kind of added to my stress at that time, was trying to learn these horribly complicated counting techniques. So I'm just saying, if you guys feel like you're going to have a nervous breakdown when you look at these, I get it. I understand. But then when I went to graduate school, I actually really put my what's the word? I just put my back into it and really learned these better than everyone else because I was so kind of trying to make up for that time in my life. And now it's one of my favorite things to do. So anyway, so this is the summary of counting techniques. So at the top here is the multiplication rule. So if you look in the left column here, that is the event. It's kind of a general description of the types of events you can count using the technique that is right here. And then on all of them, I have an example question, some example outcomes, and the answer to the example. So you can use this as a little reference sheet for you if you would like. I put it on the last page of the notes from today, if you find that helpful. So the first type of event is making a series of decisions where the number of choices available at each step does not depend on the previous decisions. So when you have that situation, you can use the multiplication rule. And so a typical example over here would be, in how many ways can a 3-letter password be made using only letters from the set A, B, C, D, E, where you are allowed to use repetition. So in all of these counting problems, it's really important that you know whether you're allowed to repeat the same element from your set or not. So like if these were people, for example, we probably wouldn't be allowed to repeat them, but because they're just keyboard letters for passwords, then we can repeat them as much as we want. So some example passwords that you could make would be like AAA, AAB, ABB, ABC, etc. So your answer here, you're going to use the multiplication rule. So you have 5 choices for each letter, 5 choices for the first letter, second letter, third letter. So you end up getting 5 times 5 times 5, which is 125. Okay, so for the second row here, the second type of event that we've learned how to count is choosing R elements from a set of N elements in a particular order with no repetition allowed. So you can actually use the multiplication rule for this too, it's fine. Or if you want to, you can use this thing right here, the P of NR, that is the R permutations, which has its own little kind of special formula. So a typical example would be, in how many ways can a first, second, and third place winner be chosen from a set of 5 contestants? So obviously you can't win more than one of the prizes. So our contestants are A, B, C, D, E again. So some sample outcomes would be like A wins first place, B wins second place, C wins third place. That would be considered different from B winning first place, A winning second place, and C winning third place. So you see that the order that you get the letters in, it actually makes a difference in the outcome. And then over here, the way you would do the answer is just P of 5 comma 3, or you could do 5 times 4 times 3, and that would be 60. Okay, so the third type of event is choosing R elements from a set of N elements in no particular order with no repetition allowed. So it's the same as the last row, except now we don't care about the order that we get the elements in. So this is the one we just went over. It is in choose R. So a typical problem here is, in how many ways can 3 winners who all receive the same prize be chosen from a set of 5 contestants A, B, C, D, E? So this is just like the committee example. If they're all going to receive the same prize, they have no special roles, then it doesn't matter what order we pick them out from the hat or however we're doing this. So some outcomes here, I've written them as sets just to emphasize the fact that the order doesn't matter, because in sets, order doesn't matter. So ABC would be one outcome, ACD could be another outcome, ACE, BCD. Those are some different outcomes. And then over here is the formula for how you would actually calculate that. Okay, and then the fourth type of event that we've learned how to count is the number of ways to do event 1 or event 2 or event 3, etc. It could be as many events as you want, where all of the events are disjoint. So this is the addition rule. And a typical type of problem here could be, in how many ways can a password with 1 to 3 letters be made using only letters from the set A, B, C, D, E? And I think I forgot to say here that we're allowed to do repetition. I'll just make a little note here with repetition. Allowed. They are passwords, so you would assume that you're allowed to repeat. Okay, so some outcomes here. So you're allowed to do 1 to 3 letters, so you could have the 1-letter outcomes here, these 5 1-letter outcomes. And then that is actually a disjoint set of outcomes from the 2-letter passwords, so AA, AB, BB. Those are disjoint from the 1-letter ones. And then the 2-letter ones and the 1-letter ones are also disjoint from the 3-letter ones, like these ones. Okay, so you've got 3 different events here, a 1-letter password, a 2-letter password, or a 3-letter password, and those are all disjoint from each other. So you're going to use the addition rule here. So this is the 1-letter passwords, the 2-letter passwords, and the 3-letter passwords. You can just add those together. Okay, and then the last type of counting technique we learned was the difference rule. So the type of event this works for is the number of ways to do one event, but not another event. And that other event has to be a subset of the first event. So you use the difference rule there. And a typical type of problem might be, in how many ways can a password with 3 letters be made using only letters from the set A, B, C, D, E with repetition allowed, but not with all 3 letters the same? So it's basically the same as the first row, except that we have to eliminate all of those passwords where all 3 letters are the same. So we can do any type of password like AAB, BBA, BCC, ABC, anything like that, but the ones that we cannot do are these 3 letters are all the same ones. So those 5 at the end there, you can't do those. Okay, so you just subtract those ones off. So that's where this little 5 over here is coming from. You're taking away those 5 possibilities. Okay, so let's do some examples from this section of the textbook. Okay, so the first example is number 2, part A. List all 3 combinations from the set x1, x2, x3, x4, x5, and deduce the value of 5 choose 3. Of course, we already know the formula for 5 choose 3, but if we didn't, we could figure it out by listing all of these 3 combinations. So this is just all the subsets of size 3. Okay, so I'm going to start with, just go in order, x2, x1, x2, x3, and I'll just do all the ones that start with x1, x2 first, so I'm basically listing them in order. So x1, x2, x4, x1, x2, x5. Okay, so that was all the ones that have x1 and x2. So now I'll do all the ones that have x1 and x3. So I already did one that had x1 and x3, so I'm going to skip over that one. That was like the first one. So I could have x1, x3, and x4. And then I could have x1, x3, and x5. Okay, and then I could have, so that's all the ones with x1 and x3. So now let me do all the ones with x1 and x4. So I already did two that have x1 and x4 in it, so I'm going to skip those. And the next one will be x5. Okay, so that is all the ones with x1 and x4. So now let me do all the ones with x1 and, let's see, actually I think I already have all the ones with x1 and x5. Let's see, I have x1, x5, and x2. I have one x1, x5, and x3, and I have one x1, x5, and x4. Yeah, so I already have all those. Okay, so now I've got all of the ones that have x1 in it. If you look at that, I think I do. Yeah, okay, so now let's do the ones that don't have x1. So if there's no x1, then I could have x2, x3, and x4. And then keeping on with the same first two elements, I could have x2, x3, and x5. Okay, so that's all the ones with x2 and x3. And now I'm going to do all the ones with x2 and x4. So basically, like, I'm keeping the subscripts in order. That's the most systematic way to do it. So if I go x2, x4, I think I have all of them already except for the one that has x5 at the end. Okay, and then that should be all of the ones that have x2 in it. So there should be 6 that have x2. Let's see, 1, 2, 3, 4, 5, 6, yeah. Okay, so then that leaves me the ones that don't have x1 and don't have x2. So that's only just x3, x4, and x5. Okay, now have I got 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep, okay. So this should be all of them. And if you look really carefully at what I've done there, not only do I keep the subscripts in order within each subset, but if you look at those subscripts as like a number, like 1, 2, 3, 1, 2, 4, 1, 2, 5, 1, 3, 4, those are also actually in order. And I just do it always systematically like that so that I can make sure I don't skip anything. Okay, so that was part A. And so this is telling me that well, I actually did it kind of backwards, right? Like I was using the fact that I knew it was 10 to make sure I'd written them all. But anyway, we can see there's 10 of them here. And then for part B, list all unordered selections of 2 elements from the set x1, x2, x3, x4, x5, x6, and deduce the value of 6, choose 2. Okay, so this is exactly the same thing, except I'm taking 2 at a time now. So this will be a little easier to do systematically. So first I'll do all the ones that have x1 and x2, or sorry, x1. So x1, x2, x1, x3, x1, x4, x1, x5, and then the last one is x1, x6. Okay, so that was all the x1s. And now the ones without x1 but with x2. So I already did one with x2. So after that is x2, x3, x2, x4, x2, x5, x2, x6. Okay, and that's all the ones with x2. So now all the ones with x3, there's already 2 up there, but I'll go from after 3 is 4, and then after that is 5. Okay, now I'll do all the ones with x4. There should be 3 up there already, but then there's also x4 and x5, and then x4 and x6. And then finally the ones with x5, x6, and that's it, because if I try to do the ones with x6, then they're already all up there already. So it makes like this nice little cool triangle thing. I don't know. All right, so how many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so 6 choose 2 is going to be 15. Okay, let's do another example. So write an equation relating p of 8, 3 and 8 choose 3. Okay, so let me just you can just look at the formula that's in that blue box on the previous slides, but I want to explain just again why that formula is what it is. So P of 8,3 is the number of ways to choose 3 elements from a set of 8 elements and arrange them in a particular order. So that's the important part. Okay, and then 8 choose 3 is the number of ways to choose 3 elements from a set of 8 in no particular order. Let's capitalize that too. In no particular order. Okay, so if we look at the difference between these two sets, what we would see is that if we take all of the R combinations and we arrange each of those R combinations in all of the possible different ways, then that would give us all of the R permutations, okay? So in the set of P 8, 3, 3 permutations, each recombination appears, and it appears a particular number of times. It appears 3 factorial times, which is 6, in each possible order. Okay, so that is why when you want to know what 8 choose 3 is, you take the value of P of 8, 3 and you divide it by 3 factorial. Okay, so that means that you're compensating for the fact that P of 8, 3 would count each of your 8 choose 3 elements 6 times. Okay. All right, so here are your homework problems. They're just like the ones that I just did. And go ahead and give these a try and check your answers in the back of the book. Okay, so let's look at some more interesting examples here. I think they're interesting. You might think they're horrible. I don't know. Like I said, these are the kind of problems that like somewhat triggered my nervous breakdown. Now I think they're fun though, so let's try them. All right, so number 7, a computer programming team has 13 members. Part A, how many ways can a group of 7 be chosen to work on a project? Okay, so part A here, I'm assuming that no one has a special role. So the order you choose in doesn't matter. Like if you're the first person chosen, that doesn't make you any different from being the second person chosen. You don't have to put this in your answer, but I'm just trying to explain it to you guys. So this is going to be 13 choose 7, like that. Okay, and then part B. Okay, suppose 7 team members are women and 6 are men. How many groups of 7 can be chosen that contain 4 women and 3 men? Oh, sorry, this is 1, not 2. So 1. All right, so we're choosing a group of 7 that has 4 women and 3 men. So this is like a 2-step decision. So now we're going to use the multiplication rule, actually. So 2-step decision. So step 1, choose 4 women. So this is where like these problems tend to get hard. It's like you have to break it down into multiple ways of thinking about everything. Break it down into steps, break it down into disjoint subsets, all kinds of stuff. So choosing 4 women, there are, let's see, how many women are there? There's 7 women, and we're going to choose 4. So this is the number of total women, and then this is we want 4. Okay, and then step 2 is going to be choose the men. So choose 3 men. Okay, so there's going to be, how many men are there? There's 6 men, and then we want 3 of them. So this is total men, and then we want 3. Okay, so the answer here is going to be, we're going to multiply these 2 steps together. So we're going to have 7 choose 4 times 6 choose 3. So that's our final answer there, and this was the final answer up there. Okay, part 2. Okay, how many groups of 7 can be chosen that contain at least 1 man? So at least 1 man, that means 1 man, or 2 men, or 3 men, or 4 men, or 5 men, or 6 men, or 7 men. So you could use the addition rule on this problem, calculate how many groups have 1 man, and then add the number that have 2 men, and then add the number that have 3 men. But I think that's too much trouble. So instead of using the addition rule, I'm going to use the difference rule. So this event of containing at least 1 man, so actually let me just write it like this. So at least 1 man is the complement, or the opposite, of no men. Okay, so what I'm going to do is I'm going to calculate how many ways there are to get no men, and then I'm going to subtract that from the total number of groups that I could have. So, so the total number of possible teams is 13 choose 7. Okay, and then the number of teams with no men is going to be, okay, so how many women do we have? 7 team members are women. So that is going to be 7 choose 7. So this is the total women. And then this is, so this is, we want 7 women. Okay, and then I'm going to subtract. So I'm just going to do 13 choose 7 to minus 7 choose 7. That's not a very good 7, but anyway, this is the final answer right there. So you take all of the possible teams, and then you take away the ones that have no men, and then that'll only leave you with the teams that have at least 1 man. Hope that makes sense to you guys. All right, let's keep going. Okay, so part B, part 3. How many groups of 7 can be chosen that contain at most 3 women? Okay, so what you gotta do here is you gotta think about what the words at most 3 mean. So at most 3 women means the following. It means 3 women, or 2 women, or 1 woman, oops, or no women. Okay, so those are 4 separate events, and they are all disjoint. So that means we can use the addition rule. Okay, so I'm going to start with 3 women. So that's going to mean there will be 4 men. So we already did that one actually, right? So there's 7 women, and we're going to choose 3 of them, and then there are 6 men, and we're going to choose 4 of them. Okay, and then 2 women, and that would be 5 men. So there will be 7 choose 2 ways to get the women, and then 6 choose 5 ways to get the men. Okay, and then 1 woman and 1 man, or sorry, 6 men. Okay, so there are 7 choose 1 ways to get the woman, and 6 choose 6 ways to get the men. And then finally 0 women and 7 men. Okay, this one actually you have to be careful because this is actually impossible. So don't let that stop you though, because that just means there are 0 ways to do it. Impossible means 0. Okay, so then what we're going to do is we're just going to add these together. So this is going to be 7 choose 3 times 6 choose 4 plus 7 choose 2 times 6 choose 5 plus 7 choose 1 times 6 choose 6. So that is the final answer there. Okay, so now let's look at part C. Suppose 2 team members refuse to work together on projects. How many groups of 7 can be chosen to work on a project? Okay, so this is interesting, and this is, I think, if I were back in the day, I probably would have gotten really stressed out over this problem, but now I think it's kind of fun. So suppose, let's give these 2 a name. So it usually generally helps things in math if you give things names. So call the 2 A and B. So how are we going to make teams that do not have A and B together? So let's think about breaking down the teams without A and B. So teams without both A and B, they can have several types, right? So there could be just A, there could be just B, or there could be neither, right? Since we have 13 employees, so we don't need either A or B necessarily. Okay, so these are actually disjoint. So there's no team in any one of those categories that's also in another category. So we can use the addition rule. There is also a way to do this. I think you could do it with the difference rule. So you could count how many teams there are that have both A and B and subtract that from the total. That might actually be easier, but let me just go ahead with this since I already started doing it. Okay, so number of teams with just A, so not B. Okay, so I know A is going to be on it, so I need 6 more people besides A. And we're going to have how many to pick from? So we're going to have, all right, so we're not picking from A and we're also not picking from B. So we have 11 left to pick from, if that makes sense, like not including A or B. So that would be 11 choose, oops, there's not a fraction in there, 11 choose 6. So the number of teams then with just B and not A. Oops, oops, my thumb is hitting the erase button. With just B and not A. That should be the same number because A and B are not like any different from each other. So that'll be 11 choose 6. Okay, and then the number of teams, oops, with neither A or B. So if there's neither A nor B, then we need 7 people, and we're choosing them from the 11 people that are not A or B. So this will be 11 choose 7. Okay, and then the total here, we just add up these 3 events. So this will be 11 choose 6 plus 11 choose 6 plus 11 choose 7. Okay. Okay, so part D is similar to part C, but like a slight variation. So suppose 2 team members insist on working together or not at all on projects. How many groups of 7 can be chosen to work on a project? Okay, so let's just, again, let's call these people A and B. Okay, so the types of teams that we can have are the following. So we can have teams with both A and B. Or we can have teams with neither A nor B. So the number of teams with both A and B. So we've already chosen them for the team, so we just need 5 more members. 5 more people from 11 remaining people. So there are 11 choose 5 ways to pick the rest of the team members. And then the number of teams with neither A nor B. So you need 7 people from the 11 remaining people that are not A or B. So that's going to be 11 choose 7. And then you just do the total. And that's it. Okay, so here's a homework problem for you to work on, and it's pretty similar to the last problem, so go ahead and give this a try and check your answers in the back of the book. Okay, so let's look at another example that also contains a couple of homework problems for you. So part A and part D, these are homework, and then the rest will be examples. Okay, so a coin is tossed 10 times. In each case, the outcome H for heads or T for tails is recorded. So for example, one possible outcome of 10 tossings could be T, H, H, T, 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 H, T, T, H. Okay, so part B, how many of the possible outcomes have exactly 5 heads? Okay, so obviously you could just kind of start trying to list these off, but it would take you a really long time, and that's not like an efficient way to do it. So we want to figure out some way of breaking down this event in such a way that we can use the counting techniques that we have. So you're trying to put 5 H's down, and then that means you're going to also need to put 5 T's down. So you have these 10 spaces where you can put them, so you're thinking about how many places can I put them. Okay, so let me write that down. So we need to have 5 H's and 5 T's assigned to 10 positions. Okay, so what I'm going to do is I'm actually going to choose 5 of the positions, and I'm going to put my H's there. So let me just write that down. So I'll choose 5 of the 10 positions to put H's in, and then I'll fill the rest with T's. Okay, so order is not important here. This is a subtle point, right? Because the order of the heads and tails does actually matter, but the order that I choose the positions that I'm going to put them in does not matter. Because no matter what order I get those positions in, I'm just going to fill them with H's, so it's going to be the same outcome. Not 10, 5. Okay, so you can think of there being like a hat or like a bucket, and I've written like 10 little slips of paper in there, and one slip of paper says the first position, and one slip of paper says the second position, and I'm going to reach in there, and I'm just going to take a handful of 5 of them out, and then whatever those positions are, that's where I'm going to put my H's. Okay, so it doesn't matter what order I pulled those little slips of paper out in, I'm just going to get the same outcome. So what I'm going to do here is the answer is just going to be 10, choose 5. So that's how many ways I can do this. All right, and then part C, in how many of the possible outcomes are at least 8 heads obtained? So part C, so at least 8 heads means the following: 8 heads, 9 heads, or 10 heads. And those are all disjoint. You cannot have an outcome with both 8 and 9 heads, for example. So these are disjoint. So because they're disjoint, I'm going to use the addition rule. So for the number of outcomes that have 8 heads, it's going to be 10 choose 8. So I'm choosing 10 of the positions to have heads. And then for the 9, I'm going to choose 9 of the 10 positions to have heads. And then for the 10, I'm going to choose 10 of the positions to have heads. Okay, then I'm going to add those up because those are disjoint subsets of the sample space. Okay, and then for part E, in how many of the possible outcomes is at most one head obtained? So at most one head means 0 heads or 1 head. And these are disjoint. You cannot have both 1 head and 0 head at the same time. So the number of ways to get 0 heads is 10 choose 0, which is actually, I believe that's just 1, because there's only one way to have no heads. You'll get that when you plug it into a calculator anyway. And then for 1 head, it is going to be 10 choose 1. Okay, so that's part E. So go ahead and pause the video and try part A and also part D, and check your answers in the back of the book. Okay, so let's look at a little geometry related example, which is kind of interesting. So we have 10 points labeled A through J, and they're arranged in the plane in such a way that no 3 lie on the same straight line. So that's important so that if we start connecting them with straight lines, we don't get any that are actually the same outcome. Like we wouldn't want to, if, for example, if like A, B, and C were in a straight line like this, then if you connected A and B, that would actually be the same line as connecting B and C. So you don't want that to happen. Okay, so I'm going to do part B, C, and D. So part B, how many, okay, so I think we need to read part A first, right? So part A was how many straight lines are determined by the 10 points? Okay, so that's your homework. And then part B, how many of these straight lines do not pass through point A? Okay, so to get a line, you know that a line is determined by any 2 of its points. So we need 2 points. Okay, so there are 9 points that are not A. And it doesn't matter what order we choose the points in, it'll make the same line. So for example, like the line BC is the same as the line CB. Okay, so then for that reason, it's going to be 9 choose 2. All right, then part C. How many triangles have 3 of the 10 points as vertices? Okay, so this is basically exactly the same as part B, except that instead of choosing 2 points, we need to choose 3 points. So same as B, but choosing 3 points. So this is just going to be 9, oops, but we're allowed to use A now, right? So we can use A. So this is going to be 10, choose 3. Okay, and then part D. How many of these triangles do not have A as a vertex? Okay, so this is same as C, but only 9 points to choose from. So this is going to be 9, choose 3. And that's it. So go ahead and pause this and do part A and check your answer. Okay, so here's one last homework problem for you to try. Go ahead and give this a try, pause the video, and then check your answer in the back of the book. All right, that's it for today, guys. It was just this one section. So I'll see you guys next time.